Hello everyone, myself Sahana from Sri Venkateshwara College of Engineering, Bengaluru. I am right now studying in first semester. My topic is vector calculus. Introduction to vector calculus. Vector calculus is a branch of mathematics focused on vector fields and differentiation. It combines concepts from differentiation and integral calculus with vector algebra. Vector calculus is essential in fields like physics, engineering, and computer graphics. Vectors and scalars. Vectors have both magnitude and direction, while scalars have only magnitude. Understanding the difference is crucial for applying vector calculus effectively. An example of a vector is velocity, while temperature is a scalar. Vector notation. Vectors are often denoted in boldface or with arrows. The notation can vary by context, so it's important to recognize the format used. Understanding notation is key when reading mathematical texts and applications. Vector addition. Vectors can be added graphically by placing them head to tail. Algebraically, vector addition is done component wise. For example, if a is equals to 2, 3 and b is equals to 4, 1, then a plus b is equals to 6, 4. Cross product. The cross product of two vectors results in a new vector perpendicular to the original vectors. It is calculated as a into b sine theta in a direction given by the right hand rule. The cross product is useful in physics for calculating torque and angular momentum. Dot product. The dot product of two vectors quantifies their directional relationship. It is calculated as a dot b is equals to a into b cos theta, where theta is the angle between them. The result is a scalar which can indicate orthogonality when equal to 0. Vector fields. A vector field assigns a vector to every point in a space. Examples include gravitational, electric, and fluid flow fields. Visualizing vector fields helps in understanding physical phenomena. Gradient of a scalar field. The gradient is a vector that points in the direction of the steepest ascent of a scalar field. It is denoted as def v, f, where f is scalar's function. Example, if f of x comma y is equals to x square plus y square, then def f is equals to 2x comma 2y. Divergence of a vector field. Divergence measures how much a vector field spreads out from a point. It is denoted as def f or def dot f and results in a scalar. A positive divergence indicates a source while negative indicates a sink. Let v of x comma y comma z is equals to x square z I cap plus y square x j cap plus y square x k cap be a vector field. Its divergence is given by capital V is equals to dou v by dou v1 by dou x plus dou v2 by dou y plus dou v3 by dou z, where v1 is equals to x square z, v2 is equals to y square x, and v3 is equals to y square x. Hence, dou v1 by dou x is equals to 2xz, dou v2 by dou y is equals to 2yz, and dou v3 by dou z is equals to 2xy. Then capital V is equals to dou v1 by dou x plus dou v2 by dou y plus dou v3 by dou z is equals to 2 of xz plus yz plus xy. Curl of a vector field. Curl measures the rotation of a vector field around a point, denoted as curl f or def into f. It results in a new vector. A non-zero curl indicates the presence of rotational motion in the field. Example, compute curl of v of x comma y comma z is equals to z I cap plus x j cap plus y k cap. Curl v is equals to matrix of dou by dou x, dou by dou y, dou by dou z, v1, v2 and v3. When we substitute v1, v2 and v3 as z, x and y respectively and solve the matrix, we get dou y minus dou y minus dou y by dou y minus dou x by dou z I cap plus dou z by dou z minus dou y by dou x plus dou x by dou x minus dou z by dou y into k cap is equals to I cap plus j cap plus k cap. Line integrals. A line integral calculates the integral of a function along a curve. It is useful in physics to determine work done by a force along a path. The formula is integration of f dot dr, where f is a vector field and dr is an infinitesimal displacement. Surface integrals. Surface integrals extend the concept of line integrals to two-dimensional surfaces. They compute the integral of a vector field over a surface. The formula is double integration of f dot ds, where ds is an infinitesimal area vector. The fundamental theorem of line integrals. This theorem relates line integrals to gradient fields. It states that if f is the gradient of a scalar function, the line integral depends only on endpoints. This simplifies many calculations in vector calculus. Green's theorem. Green's theorem relates a line integral around a simple closed curve to a double integral over the region it encloses. It is a special case of the more general Stokes theorem. This theorem is useful for converting complex line integrals into simpler double integrals. Stokes theorem. Stokes theorem generalizes Green's theorem to higher dimensions. It relates a surface integral over a surface to a line integral and around its boundary. The theorem is crucial in fields like electromagnetism and fluid dynamics. Divergence theorem. The divergence theorem connects surface integrals to volume integrals. It states that the total divergence of a vector field within a volume equals the flux across the boundary. This theorem plays a significant role in physics, particularly in the analysis of fluid flow. Application of vector calculus. Geodesics on a surface. Electric field from distributed charge. Plotting a slice of a vector field. To find the rate of change of the mass of a fluid flows. In rigid body dynamics, in rectilinear and plane curvilinear motion along paths, and in both rectangular. Applications in engineering. In engineering, vector calculus is used to model systems and analyze stresses and strains. It aids in understanding fluid flow, structural analysis, and heat transfer. Engineers utilize these principles to optimize designs and processes. Conclusion. Vector calculus is an essential tool in understanding and modeling multidimensional phenomena. Mastery of vector calculus concepts is crucial for success in various scientific and engineering fields. Continued study and application of vector calculus will enhance problem solving skills in mathematics and beyond. This structure covers various aspects of vector calculus, providing a comprehensive overview with images, while adhering to the specified images can be added to each slide for visual representation of the topic and discussed. Thank you.